All right, so let's walk through one of these with some actual data. So example 7.3.1, test of the mean using t-test. So a random sample of 20 IQ scores of famous people, so already we've got a little n given to us here, was taken from the website of IQ of famous people, and a random number generator was used to pick which 20 to use. Do the data provide evidence at the 5% level, so there's alpha, that the IQ of a famous person is higher than the average IQ of 100. So they give us a table here that has the IQ scores for the famous people that they collected them from. Those are our 20 randomly selected data points that we could put into L1. Okay, so if we hit stat and 1 to get into that list screen and to put those 20 data points into L1. All right, so a hypothesis test. Again, we're going to use the acronym PHANTOMS again to get all the parts in all the right places. So P stands for parameter. So again, we're dealing with quantitative data, which again, there's lots of parameters for quantitative data, but for this intro course, it's going to be the mean. So for quantitative data, our parameter is going to be mu. So this is going to be the mean. And then the variable we looked at here was IQ score. And it's for the population, because mu stands for population mean, so of all famous people. Okay. That's the value that we're going to test in the hypothesis, and we're going to get information for that from our sample value of x bar. So in words, x bar is going to be the mean IQ score of 20 randomly selected famous people. All right, so the H in PHANTOMS stands for hypotheses, so we're going to set up the null and alternative hypotheses. So H sub 0 is going to be that mu equals 100, and the alternative, we wanted to show that this mean IQ score was higher than 100, so greater than 100. And the level of significance that we're going to use to make our decision in the end, they told us to use 0.05. Now, the level of significance is not always 5%, but it is the most common one, which is why it's what we used in the last unit to define that difference between unusual and not so unusual events. All right, our next letter is A for assumptions. So again, remember these assumptions will be on your cheat sheet for the exam, so you don't need to memorize them. You just need to know which tests to use, which ones, and what all the symbols stand for and what the words mean. So a random sample size n is taken. So if we go back up to the paragraph, they used a random number generator to pick those. So a random sample of 20 IQ scores was taken. And again, these conditions are different than the last one, so we're not looking to put one object into one of two categories like we were with the qualitative data in the last one. So our next one, second condition here, we either need a population that's normally distributed or we need a sample size that's at least 30 with no outliers. Okay, so this happens to be data that we looked at back in example 6.4.2. Okay, so on this one we have data, so we could run the checks on the data. Okay, so in this case we made a histogram and it was roughly bell-shaped. So we're not going to repeat all of those here. So if you need to, you can go back and look at 6.4.2 example to see those. And then we made a modified box plot. And there were no outliers. And we also made a normal probability plot, and that was roughly linear. So because all of those conditions checked out, it's reasonable to assume that this data came from a normal population. Okay, so in here we either need a normal population or a sample size of at least 30. Well, we don't have a sample size of at least 30. They only took 20 IQ scores. but it's an or statement, so we just need at least one of these things to be true. And so it is reasonable to assume that the data came from a normal population. And then sigma has to be unknown. So sigma was not given, and you can't get it from sample data. So be a bit careful when you put data in L1, and if you do one variable stats, the calculator doesn't know if it's population or sample data. So on the output screen, it's actually going to show you a value of sigma and a value of S. Okay? If what you have entered is sample data, you have to disregard the value of sigma. And if what you entered was population data, you disregard the value of S. Okay, so if sigma's not given and all you have is sample data, you can't get it from sample data. So sigma is unknown in this case. All right, so our next check here, next letter is N to name the test that we're going to use, and the conditions here are met to use the t-test screen. Okay. All right, so now T stands for test statistics. So again, we're going to go into our calculator. We already input the data into L1. Okay, so we had to do this first. Okay, so it's not going to make any sense to tell the calculator to use L1 unless it has the correct data. So if you did not enter the data into L1 at the start of the problem, you would need to do so now before continuing. But then in this input screen, we would highlight data instead of stats. Our null hypothesis here, mu sub 0 is 100. Next to list, we would type L1, second function 1. Frequency, the default there is 1, and we're never going to change that, so that should say 1. And then here, again, we pick what our alternative hypothesis is, so we're going to choose mu is greater than mu sub 0. And then when we highlight calculate and hit enter, this is what we should see for our output screen. So again, the first line here we should always check before looking at the rest of the numbers to make sure that we highlighted the correct inequality. So our alternative hypothesis here is that mu has to be greater than 100. So this does match. So here is our test statistic, our t-score. Here is our sample statistic x bar. And here, where it says p, we need to keep in mind that is not p, but it's actually a p-value. So all of the numbers that we need are here on this output screen.